Any questions over Monday's discussion? None? So this is the first thing that came off the top of my head as far as what we went over Monday. So what do you know about NBS? Bromination, and notice I have a double bond there. Does it go on the double bond or somewhere else? It goes on the allylic position. All right, next up, now what happens? We got a strong nucleophile, has a negative charge. It's not a strong base. So what kind of reaction do you expect next? SN2. So next up, I'm gonna go crazy. All right, so what happens after it's step 3? Notice it's just aqueous acid. Aqueous means hydrolysis of the cyanyl group. Hopefully it's not gonna mess up that double bond. Well, let's just pretend that that's not an issue. So just keeping with the topic of the chapter. All right, then what's the thione chloride do? Can we name all these? This is kind of incomplete down here. All right, onward and upward. Boiling points of some of these derivatives we were looking at. So my favorite question, they chose here things that nominally weigh the same, 55 to 60. Why did they do that? They want to keep what intermolecular force constant? Yes, London dispersion. We want to make a comparison here. And in fact, here's some different molecular weights. Here's our acid chlorides. Here's just straight chain alkanes, boiling point, molecular weight. So we're here at 60-ish. And this is even higher than this thing here. And to me, the first time I saw this, I'm like, that is very curious. This thing can hydrogen bond. This thing can form a dimer with itself. Carboxylic acid chapter said all carboxylic acids are soluble in organic solvents because they can form a dimer. Let me see if I can illustrate that. So maybe we have a big long chain. So there's this hydrogen bonding forming the dimer. So you'd think with this big polar thing that at least something as short as acetic acid wouldn't be too soluble in benzene or something. So here's this dimer forming with hydrogen bonding. Is this so high because I got 2 hydrogens on this nitrogen can hydrogen bond with another oxygen? So this can undergo hydrogen bonding as well, but the other day we saw something interesting, and that was the resonance of this. Monday we found out that this lone pair isn't as basic as it should be. We should be able to plop a proton on there, and it doesn't like to do that because there's this double bond character here as seen in the resonance structure. So in addition to this hydrogen bonding that we got going on, we also have this dipole interaction. Here's the negative oxygen and the positive in this thing. The resonant picture of an amide shows its strong polar nature. Hydrogen bonds and dipolar attraction stabilize the liquid phase, resulting in higher boiling points. So if you ever needed physical evidence to convince somebody of a hybrid resonance structure, now I imagine this might be said to be the major contributor and this one the minor, but this physical property here of these being way up there, these probably drop down to steric hindrance, and as you get to a tertiary, they can't get as close. So here we see melting points. This looks like a boiling point. 80 degrees Celsius, very high boiling points and melting points. Compared to other compounds of similar weight, melting points increase with increasing number of nitrogen-hydrogen bonds. Acid chlorides and anhydrides are too reactive to be used with water and alcohol. Esters, tertiary amides, and nitriles are good polar aprotic solvents. Solvents commonly used in organic reactions. Ethyl acetate, dimethyl form amylide. With our nomenclature, we ought to be able to write this formula or structure. Dimethyl form amide, acetonitrile. This has got to be a common name. Well, why don't I do the Lewis structure? So ethyl acetate, not totally soluble. You can make a 5% solution, 8% solution. Can't make a 20% solution. The rest of these totally miscible with water. Of course, we can dry these and use them in situations where we don't want any water. So in case we missed it in the IR chapter, carbonyl carbons, that one of the most strongly absorbing peaks in 1710, 1720, normally what I think of. And as we see that shift to the left or to the right, we can figure out what's going on. Esters shift to the left at a higher wave number. Amides shift over to the right, a little bit lower. Acid chlorides, there's something that's shifted way to the left. Acid anhydride, and then the nitrile is a sharp, moderate peak there. So when I look at this and don't know anything about it, I say carbonyl carbon, and then I go 17, I'm only getting to 20. I don't like the graphic. But anyway, it shifted over a little bit, and the stretching table I put on the back of quizzes says 1735 is where you see an ester occur. Lactones and lactams. The lactone is a cyclic ester and the lactam is a cyclic amide. So here, no strain, perfect hexagon. There's what that truth table says for an ester. So it becomes more strained. The wave number goes up. See the same thing here that's shifted over to the right below 1710. But as we add more ring strain, so ring strain and lactones and lactams increase the carbonyl stretching frequency. Here's an anhydride. I don't know what to make of this. Maybe it's like an overtone, or I don't know why there's two of them. All right, proton N.M.R. Remember, aldehydes are highly deshielded, way downfilled, and 4 here. So what's the acronym for this compound? D, di, M, methyl formide. How many carbons? 1, 2, 3. To me, they look chemically equivalent because that bond rotates. According to this, I have 1, 2, 3. Interesting thing about carbon NMR, how many hydrogens? I just see 3 in our carbon 13 NMR. That's where we're going to see these. Carbonyl carbons of acid derivatives appear at shifts around 170 to 180 ppm, slightly more shielded than carbonyl carbons of ketones and aldehydes. Alpha carbons absorb around 30 to 40 parts per million. Any questions?